Lecture 34, The Strength of the Crust. We have looked at the response of rocks to stress and their strength, mainly in laboratory experiments. In this lecture, we will look at these rock properties at a larger scale. This diagram shows the transition from intact rock to heavily jointed rock mass, with increasing sample size. As the size of the rock sample increases, the mechanical behavior of the rock mass is more and more controlled by discontinuities, and its strength decreases because of these discontinuities. The strength of the intact rock or a discontinuity plane can be calculated with laboratory or in situ tests. However, with respect to the rock mass, their dimensions and natural conditions cannot be reproduced in the laboratory, and there are no appropriate methods available for estimating its strength in situ. This is why the strength of rock masses must be estimated using indirect methods such as rock quality indexes, mathematical models, and scale models. This diagram shows the change of a cube as the length of its side is changed. Increasing 2 times the side increases 4 times the area, and 8 times the volume of the cube. Increasing 3 times the side increases 9 times the area, and 27 times the volume of the cube. And so on. Now suppose the cube is rock. The strength of the rock is proportional to the area of the cube, since strength has units of force divided by area, and its weight is proportional to the volume of the cube. Therefore, by doubling the size of the cube, its weight-to-strength ratio is doubled. Increasing the side of the cube by 3 increases the weight-to-strength ratio by 3, and so on. This means that as the rock sample increases in size, it becomes weaker. This is because for any increment of size, the increment of weight is larger than the increment of strength. In 1945, the geologist King Hubbert posed this interesting question. If we had a huge crane, can we lift the state of Texas as indicated in the figure? The answer is no. At this large scale, the state of Texas would be so weak that to lift it up, we would need to shovel it. To understand why, one just need to realize that the pressure at the base of such big block of rock would exceed by a factor of 45 its strength. This is the reason we can use dry sand in centimeter scale models to simulate kilometer scale rock structures. These scale models are known as sandbox experiments. Here is one example. The upper figure is a seismic section of a kilometer-long structure in offshore Morocco. The lower figure is a centimeter scale sandbox model of a similar structure. The length ratio between the actual structure and the sandbox experiment in this example is about 10 to the 6. Therefore, the strength of the material in the scale model should be about 6 orders of magnitude lower than the strength of the rock. Dry sand has approximately that strength. Now, let's look at the variation of rock strength with depth in the upper crust. The rock strength values here are from laboratory experiments and small-size rock specimens. The green field is the tensional strength, and the blue field is the compressional strength. As you can see, rocks are stronger in compression than in tension. Dry rocks are stronger than wet rocks, and for the case of shale, fluid pore pressure, as expressed by the fluid pore pressure ratio lambda, decreases strength. Salt is special. It has little strength at shallow depth, and very little to no strength below 2 km depth. Notice the blue curve labeled dry limestone. At 8 km depth, the limestone behaves mechanically differently. In fact, if we look at the crust, we will see that the upper crust behaves brittly and follows the Coulomb failure envelope. This is represented by the 3 curves labeled by faulting mode, reverse, strike-slip, and normal. Notice that reverse faults are stronger than strike-slip faults and normal faults. We will discuss later the reason for that. The crust below 10 km depth or so behaves in a different manner. The strength follows the red curve of plastic deformation. This curve is controlled by factors such as rock composition, temperature, and strain rate, E. Lower strain rates move the red curve up, because the rock is weaker when it is deformed slower. The intersection between the blue and red lines defines the brittle plastic transition. If we look at the continental lithosphere, which includes the crust and the lithospheric mantle, we can reconstruct the strength profile as indicated in Figure A by combining a brittle failure envelope, which is the blue line, a quartz plastic flow law for the upper crust, a feldspar plastic flow law for the lower crust, and an olivine plastic flow law for the mantle. This results in different strength profiles for the upper crust, lower crust, and mantle. Figure B is for wet rocks, and Figure C is for dry rocks. Notice that dry rocks are stronger than wet rocks. Let's focus on the strength profile for dry rocks. The upper crust is brittle, and the middle crust is plastic. The upper part of the lower crust is brittle, and the lower part is plastic. And the upper part of the lithospheric mantle is brittle, while the lower part is plastic. This model is humorously referred to as the jelly sandwich model. The bread slices are the brittle parts of the lithosphere, and the jelly layers are the plastic parts. The jelly sandwich model has been confirmed to some extent by the velocity of seismic waves through the lithosphere. Seismic waves travel faster in the bread layers than in the jelly layers. This model is important for understanding lithospheric scale deformation. To learn more about this, read Chapter 6 of Fossen, and do his e-learning model on rheology. And answer these questions.